Let's now move on to our next talk by Norbert Schorghofer. He will be speaking on what ice on Ceres might tell us about ice on the moon. So, Norbert, are you there?
Yes, can you hear me and see my
Yes.
slides?
We see you, but we don't see your slide yet.
Oh, I haven't turned on screen share, I guess. Um,
And it's trying. It will be there soon.
okay.
Here we go.
How about now? No?
Yep, looks great. Thank you.
You see the slides?
Yes.
Okay. So, so Ceres is, of course, the largest of the asteroids, and it's also a dwarf planet. And it's still much smaller than the Moon and Mercury, but it has several closely related properties. And one is it has permanently shadowed regions. So its axis tilt is only 4 degrees, and so it provides a great comparison to the permanently shadowed regions of Mercury and Earth's moon. And it's an ice-rich object to begin with, right? So it's sort of always been understood from its low density, and now so Dawn has explored Ceres from 2015 to 2018, so we understand so much more about it now. And so here's a graph of modeled temperatures, and the average temperatures are pole world of about 75 degrees or so. The average temperatures are 110 Kelvin, right? So although these are sunlit regions still, this ice-rich area is has a similar temperature than the mean temperature than the lunar cold traps have. So there's some analogies, and we can perhaps learn something from Ceres about the cold traps on the moon, or icing cold traps on the moon. And so one of the well, there was a surge of ice on the surface of Ceres, and almost none was found. So this famous bright spots in Ceres, which have even some of them have even been seen from Earth, which turned out to be mostly salt. And so eventually some ice was found, and it's in I don't know if you can see that. Seems to be a delay in the slides. That there's a wide region which I'm trying to point at here, close to a rim of a crater and so on, where a spectrometer picked up some water ice, and eventually a few spots were found, which are partially water ice, but very small. The largest water ice deposits on the surface of Ceres are actually in the permanently shadowed regions. So it's almost completely ice-free, and yet it's an ice-rich object. It's a strong contrast, and of course a way to look at the near subsurface is with neutron spectroscopy. So the grand instrument measures the neutrons coming back, and if there's lots of hydrogen nuclei, these neutrons get slowed down faster, and so it reveals the concentration of hydrogen, and there's a big north-south gradient in the hydrogen concentration, but not longitudinal, right? So this is what that expects, exactly what one expects from a temperature-controlled ice table. So that really shows the top meter of Ceres ice-rich, and equator it's probably just a bit lower than that. And in the polar regions, and if one matches that with models in the polar regions, we're going to find ice within a top centimeter, right? So there is this huge contrast between what the surface looks like, almost completely ice-free, while you have an ice-rich, even on a global scale, an ice-rich subsurface. And I think that has some implications about strategies for mapping lunar ice on the moon. because it may well be just in a subsurface, and the absence of ice on the surface, apparently. So this is sort of a reminder from reality. The absence of ice on a surface does not at all exclude an ice-rich subsurface. And why is that? So here is a result of a model calculation, and this is actually not for Ceres but the moon. And the surface temperature are actually temperatures measured by Divina. So both, which is an instrument around the moon which measures the temperature, and so it includes diurnal as well as the seasonal variations. So these are great surface temperatures. And then there is a numerical solution to what the subsurface profile, temperature profile will look like. And then the bottom panel shows the sublimation loss rate in kilograms per square meter per gigayear, right? So 1,000 is about a meter of ice. 10 to the freeze about a meter of ice at sort of a random location in the polar regions. And so, within 10 centimeter depth, the loss rate is reduced by 9 orders of magnitude, 9 orders of magnitude. So if a frost patch on the surface lasts for a year, it's going to last 1 billion years at 10 centimeter depth, right? And that's because there's a diffusion barrier, but also more importantly, because it's high peak temperatures of a surface do not penetrate to great depth. So, subsurface ice is just much more stable, and sort of a surface is a last place to expect ice. And so then the other interesting analogy to the moon are the cold traps, right? So here's a nice 3D image, and the cyan areas here are the cold traps of Ceres, which have been mapped in 2 ways now. And so this is an animation of a permanently shadowed region on a Ceres. I don't know how well that comes through, but this is also actually, there's a bunch of images taken near summer solstice. So the floor of this craters is really permanently shadowed, or perennially shadowed at least. And that's because the axis tilt is only 4 degrees, at least currently. And then, and this is then a map of permanently shadowed regions made by using topography made by, for stereo imaging when running a model. And these are permanently shadowed regions. Their number or the fractional area sort of similar to the moon. And then quite quickly, actually, bright deposits was found in some of them, but only some. And one of these bright deposits actually sticks out, was spectroscopically identified as water ice. And so, so there appear to be some, most likely ice deposits in them, but the mystery was why only in some of them. And the answer was sort of found in the history of the axis tilt. So the axis tilt of Ceres actually varies, which we can also now backwards integrate between 2 and 20 degrees, sort of. Currently it's 4 degrees. And so when it goes up to 20 degrees or 90 degrees, these persistently shadowed regions are smaller, and there are some which are really permanently shadowed for billions of years. And the bright deposits appear to be closely related to the areas which are really permanently shadowed, not just currently shadowed. So but sort of, to the degree we can determine good evidence that these are indeed, this is a cold trapped ice. In a sense, it's so cold there, never leaves it once it falls in. And so what it means is cold trapping works on Ceres. It also works on Mercury, we know. And so the question is, why would the moon be any different? And the simplest answer to that is the moon is not different, but the cold trapping also works on the moon. It may just, how many? Okay, was this 10 minutes? Okay.
Yeah, 4 minutes left.
Okay, so so cold trapping. So oh yeah, I should show this slide here. So cold trapping works on Mercury, as it's been worked out fairly well, corresponds to radar bright features and other evidence. And it seems it also works on Ceres. And so the moon may just have a lower supply of water, at least a recent supply of water, right? Because all the cold traps got erased when a spin flip the moon underwent about 2 billion years ago. The recent supply of of water to the moon may have just been less than on Ceres and on Mercury. And there is, I know at least two plausible reasons why this may be the case. And if cold trapping works on the moon, there is ice in every cold traps. So conclusions: just because the surface has almost no water ice, doesn't at all exclude that there is a rich ice-rich subsurface, shallow ice in a subsurface, with implications for what technique we would choose to map ice on the moon. Then, well, I didn't say that, but of course, Ceres is being bombarded by impact for its entire history, and yet there is still ice in a top meter, probably even a top few, decimeters and centimeters. And impacts have two rows, right? They can devolatilize, they can also recharge, and we don't quite understand this yet. But apparently all this impacting did not get rid of its ice. And that may also be a lesson for the lunar cold traps. And finally, because cold trapping works in Ceres and Mercury, there is even better reason to believe it also works on the moon, which would imply there is water ice in some water ice in every single cold trap on the moon. Thank you.
Great, thank you. Very nice talk. We have time for some questions. So any questions online, or anybody want to raise their hands? I have one. Interesting, the correlation or the comparing the moon to Ceres. But one difference is temperature, right? Ceres is at 3 AU, something like that. Surface temperature is much colder. I'm not sure if you talked about that. Could you speak a little bit to that and the possibility of cold trapping other volatiles in these PSRs on a Ceres versus the moon?
Yeah, so currently, under its current obliquity, some places will be cold enough to trap CO2 and maybe what's the other one? Whatever is next on a list of volatilities. But at 20-degree obliquity, it seems only water ice can be trapped. So so under current conditions, yeah, it looks like can trap. I mean, it's a simple estimate using a parabolically shaped crater, right? Then you can easily calculate the temperature. So currently, it seems to be able to trap other volatiles, but probably not throughout. Probably not. The axial variations are about 24,000 years. So over that time scale, other volatiles may get erased.
Okay, thank you.